Ladies and gentlemen, we start the last day of the conference with a presentation from Dafnis Krasniqi,
Yes.
and will talk to us about the Hurdle models and the statistical learning Hurdle models, so estimating phi, accident frequency. So, and the place setting.
So, hello everyone, happy to be here today. So, today I'm going to talk about the parametric Hurdle model and statistic learning Hurdle model for estimating frequency accident. So, I am a PhD student at the University of Paris 1, Panthéon-Sorbonne, and for my PhD, I have a partnership with a big company called Alliance. And I spent some time in my laboratory in the university and some time in my company, so I have a partnership with this. And today I'm going to talk about count data. Okay, so here's the overview of my presentation. So I'm going to talk about my motivation for this work. Then I'm going to talk about the Poisson Hurdle model. Then I'm going to talk about the Hurdle model with statistical learning. And finally, I'm going to apply these models to a real database and to see what's happened and to check the performance. So my motivation for this work, so I work in an insurance company and we have a lot of count data for claims. And when you have count data, we work always with Poisson Hurdle, with Poisson regression, classic Poisson regression. We use a GLM, generalized linear model. And sometimes we have some problems because we have an excess on the zero. And in this case, we have a big problem because we have some over-dispersion. And what is over-dispersion? That means that the expectation is lower than the variance. And in this case, we can't use anymore the Poisson, the classic Poisson regression. And we need to change the model. There are several models to handle this problem. So we can use the negative binomial model. We can use the zero inflat model. Or we can use the Poisson Hurdle model. Okay. In my case, I choose to work with the Poisson Hurdle model, and I'm going to present it in detail in the next slides. Here we have the distribution of the Poisson Hurdle model. It's a very simple model. It's worked with two different models. So, okay. Here we have the the red light.
I don't know if do we have that?
Okay. The red one. Great, thank you very much. So here we have the first model. So the Hurdle model is with two different models. So the first model is the binomial model, a binomial regression. Okay, this model is going to be trained on a binary target. So we have the first target is this x0, all right. So it's the first class, and the second class is the positive values, all right. And this model is going to be used with a logic link. So finally, we are going to have the probability to be 0 and 1. The second model, it's a zero truncate Poisson model, all right? And this model is going to be trained only on the positive values, all right? And for this model, we use a log link, all right? So this is a classic Hurdle model. And here we have the expectation, the variance of this model. The expectation is very simple. We're going to multiply the probability to be in the positive case by the expectation of the zero truncated Poisson model, all right? So here we have something between 0 and 1, and here we are going to have something greater than 1, right? And we are going to multiply these two things together to have an expectation. Here we have the variance of the model, and we can see that the expectation is lower than the variance, so this model can handle the problem of over-dispersion. So it's very nice for our case. So to estimate the different beta of the model, we are going to use a classic tool in statistics. It's called the maximum likelihood. Right. So here I have the log likelihood of my Hurdle model. All right. This is this thing. All right. And of course, with some mathematics, we can separate it into different log likelihood. All right. The first one is the log likelihood for the binomial case. Okay. No, this one is for the binomial case. And the second log likelihood is for the Poisson zero truncated model. All right. So instead of using the whole log likelihood, we can separate it in two different log likelihoods. All right. And we can estimate the beta hat, the vector of beta hat, by maximizing each log likelihood. similar thing, all right? We can do it with using different algorithms, right? We can use the Gaussian-Newton or the Newton-Raphson algorithm. And to choose the best combination with for the numerical and categorical features, we can use some criteria like the AIC or the BIC, some very, very classic. But with my supervisors, we ask ourselves if we can improve this model. So the proposal is, can we replace these two models, these two classic models, the binomial and the zero-truncated model, by two non-parametric models? This is the goal of the second section. And for the non-parametric model, I choose to use the XGBoost model. Of course, we can use any other model, but in my case, I choose this one because I know it very well and I work a lot with it. So, of course, we can use neural nets, other things, but I choose XGBoost. It's a very, very powerful library. We can do both regression and classification tasks, so it's not a problem. It's work with a loss function, right? And the goal is to decrease this loss function by adding some trees successively. Right? So we add the trees, and the goal is to decrease the loss function. The big problem with this library is overfitting. So we have a big chance to overfit. So to avoid this problem, we use a lot of regularization. Right? We can use L1, L2, or both of them. We can also use yield stopping or something like this. All these tools to avoid the problem of overfitting. Right? So here is the first model. So I'm going to replace the binomial regression by a XGBoost binary. Right? So here's a new target variable. So y star is defined for 0 and 1. 0 for the excess on the 0, right? And 1 for all the positive values. Right? And here we have the loss function for this model. And of course, this loss function is very, very close to the log likelihood in the regression part. But instead of using parameters, we are going to use trees to minimize this function, this loss function. And of course, to have something between 0 and 1, we are going to use we are going to put all our trees that we build with the XGBoost in a sigmoid function. And so PML is going to be something between 0 and 1, like in the classic case. Okay. And PML is going to be the probability to be in the class number 0. And 1 minus PML is going to be the probability to be in the class number 1. The second model, so we are going to apply the second model also. So here we have the target variable for this model. It's y tilde, and y tilde is only defined for the positive values. Right? And here's the loss function for this model. This loss function is also very, very close to the log likelihood of the classic model, but instead of using classic parameter beta, we are going to use some trees here to decrease this loss function. The big problem is that such a function doesn't exist in the library XGBoost. Right? So the goal is to code a new loss function in this library. And to do that, we need three different ingredients. We need the first derivative of a loss function. We need the second derivative of a loss function. And we need the evaluating function. And in this case, we are directly using the loss function. So the loss function is going to be used for training the model and to evaluating the model. Okay? And to have something greater than 1, we are going to use exactly the same expectation that for the zero-truncated model. But instead of using lambda e, the parametric parameters, we are going using our different trees that we built with the XGBoost, right? And in this case, we have something greater than 1. Okay. And finally, our final output of the model is going to be mu hat, and mu hat is going to be the probability to be in the case 1, so in the positive case, and I'm going to multiply it by the output of my zero-truncated XGBoost. Alright? And this one is exactly the expectation of the classic hurdle model. It's the same thing. Alright? So the final thing, I'm going to apply this to a real database for a real company. So here's my database that I have. So it's a public database from a French company. Here's my target variable. All right. So here I have the 677,000 drivers in my portfolio. All right. And here's the claims. So I have drivers between that have 0 or until 5 claims. All right. So it can be 0, 1, 2, 3, 4, 5. And here are all the other features that we are using to train our model. All right. Here we have the claims. All right. We're just looking at the target variable. You can see that we have a big excess on the 0. Okay. We have a lot of drivers without any claims. It's a good thing. We have some drivers with one. We have 32,000 drivers with only one claim during the year. We have 1,784 drivers with 2 claims in the year. We have 82 drivers with 3 claims in the year, and so on. So 7 drivers with 4, and 3 people with 5 claims in the year. And our goal is to have the expectation of claims for each driver based on his futures. Right? I just explain what we are doing with this thing after in your company. For instance, when you call your company and you want insurance for your car, they are asking you a lot of futures, where you're living, your age, the brand of your car, and all these things. And they are computing 2 things with all your futures. They are computing. They are computing 2 things. Mu for the frequency, so this one here for the claims. And they are computing another thing called mu cost. Okay, and with these 2 things, they are computing your premiums, right? That you are paying for your insurance, right? So this thing is very, very important in our company, and we need something very, very precise, right, for all our clients. To compare models, for different models, we are going to use 2 different measures, right? We are going to use the deviance, the Poisson deviance. It's a very classic tool when we use down data. Right? And the second metric that we are using is the difference between the prediction of our model and what we see in your database. All right. When we compute the mu f, we are always having something positive. So the good driver are going to have something close to 0, but never negative or never 0. Okay, because it's not possible. Because the price of the insurance is going to be 0, so it's not normal. So we have always something greater than 0. Okay? And here are my results with the cross-validation with k equals 30, and we can see that the model. Here I put some other models in the literature, right? I put the classic Poisson regression. Here we have a single tree. Here we have a Poisson boosting model with depth equal 3 and 5 here, and we can see that the hurdle model built with machine learning, it's better than the other models, and especially that classic hurdle model. And we can see that we are very, very close to the real number in the database. So it's a very, very good point. And I have 30 values, so I can draw a box plot. So here's the box plot of the different models that I built for the database. And you can see that the model I built with the whole model I built with machine learning, it's better than the other models. That is that.
My presentation. Is there any question from the audience? One.
So I have questions. First one is, I was wondering why you need to go for a Pareto-Poisson model at first? Because if I understood correctly, you want to predict future trend that could possibly happen, but didn't happen in the historical data. And I believe that if we have, for example, a limit of claims we insure, we can use Pareto to be able to, a curve fitting Pareto.
I don't know.
Okay.
I know that in my company we use only Poisson regression to do all these things. So the whole thing is done with Poisson regression and nothing else.
Okay.
Okay. So I heard about the Pareto, but we never use it in our industry. So I don't know what to say. So.
Okay. And second question, you don't add in your model the amount, the average amount of claims, of claim amount.
No, it's another model. If you want to compute the amount of the claims, it's another model. It's a gamma model. So we use another model to train our model on this data. So in this case, I train only the model for the frequency of the claims. If you want to have the prediction of the amount of each claim, the expectation of the amount for each claim, we use a gamma model. So in this case, I don't talk about this the second part of the premium. I choose to talk just about the first part. So,
Is there any other question?
So if I understood correctly, you are using XGBoost to learn about the most important features for the predictions, which will give expectation strictly greater than 0, right?
Yes.
Okay. So now, like, so it's kind of like you are trying to learn from the features which are the outliers based on the features, right? Okay.
It's a very, very big, difficult problem because we have a lot of zeros in our database, and and it's very difficult to find some people with positive claims. So it's why we work always in average here. We take the average of claims for each driver.
And the number of features are always like this, or they can be
no, I
have
have
more.
It's a public database, but in practice we have hundreds and hundreds.
And you use the tree to learn about
the tree choose itself all the features that they need, and of course here in this case the good drivers are going to pay something, of course.
And what is your time frame of the observation? The time frame of your observation for the claims.
Here we have something called, I don't talk about it, we call it the exposure. Right?
Okay.
Because we have some people in our database who leave the company, who are coming in the company during the year. So the exposure is going to be something between 0 and 1. Right? So if the driver leaves the company in June, and he stays from January to June in the company, the exposure is going to be something between 0.5. Right? Because he stays in the company for the half of the year. Right? If he comes in the company in July to December, the exposure is going to be 0.5 also. Right? And this thing is very, very important in your model because it's a way for the driver. Because having a claim in 6 months and having a claim in 1 year, it's not the same thing. Right? This variable, I don't talk about it, but it's a sort of weight in our industry.
Okay, thank you.
Okay. Is there any other question from the room? Looks like no. And then I will let's thank the speakers once again.